Hello. Today we present Ultra, a university-led team builder from requests for proposals and analysis. The outline of this presentation is as follows. Objectives, use cases, methods, goodness score, human study, and finally, a live demonstration of our tool. Ultra is an AI-based prototype system that is used to assist in team formation when researchers respond to requests for proposals, or RFPs, from various external funding agencies, such as NSF or NIH. The aim of our work is to present novel methods and useful tools for group recommendation with fairness. The inputs to our system consist of the requirements set forth by RFPs and profiles from researchers. The output is a list of N teaming suggestions, where a user has the option to accept or reject. We identify at least 3 practical use cases of our system. Use case 1. Given a researcher's name and a matching method, we show a list of N highest-ranked proposals and candidate teams along with goodness scores. Next, we have use case 2. Given a proposal and a matching method, show a list of N highest-ranked candidate teams. And finally, use case 3. Given a research interest and a matching method, show a list of N highest-ranked proposals and candidate teams. We use 4 matching methods to form teams. The first method, M0, is random matching, also which we use as our baseline. For every proposal, M0 selects researchers and forms teams randomly without any reference to any one specific skill set or the proposal's requirements. Our second method, M1, is string matching, where we consider a proposal's requirements and every researcher's interests, and we check if there is any overlap between those two using a string match threshold. The third method, M2, is semantic matching, where we consider an ontology classification from ACM to determine if 2 interests have any broader similarity than just string matching. For instance, the keyword learning can also fall under artificial intelligence. While M1 would not be able to distinguish this difference, M2 will. The final method, M3, is boosted bandit matching, where we use a contextual bandits algorithm for relational domains based on relational boosted trees to determine the best fit researchers for a given proposal. We use 4 metrics to measure the quality of each candidate team and compute an overall goodness score using them. The first metric is redundancy, which is defined as the percentage of proposal-required skills that are commonly shared by multiple researchers. The second metric is set size, which is defined as the number of members in each candidate team. The third metric is coverage, which is defined as the percentage of proposal-required skills that are satisfied by a candidate team as a whole. The fourth and final metric is K robustness, which denotes a team's reliability should any of K researchers become unavailable at any given time. We build a UI to represent our system and conduct a university IRB-approved study to ask participants for feedback on all use cases and displayed results. We pose 2 questions in our survey. 1. How relevant is the output given the input? And 2. How useful is the output? We also provide a section for additional comments, if any. We will now give a live demonstration of our tool. We show 3 use cases to demonstrate the utility of our system. Each use case has various input prompts to select from, and each of them have 4 different methods that can be used to recommend or suggest proposals and teams to interested users. In use case 1, we have the option to select a researcher from the drop-down list. Select one of the following matching methods and input how many proposals and teaming suggestions the user would like to be displayed. We choose any of the researchers first. Next, we show results for method M0, where teams are randomly formed. We select to display 5 proposals and 3 teaming suggestions for each proposal. Each team displayed here also has a match score in descending order, denoting the likelihood of the team's success towards the corresponding proposal. On the left, we extract the skills needed for each proposal, which serve as an explanation as to only why certain teams are formed. While M0 does not consider this aspect, M1 to M3 do. Similarly, for the same researcher, we select the string matching method this time, M1. Compared to M0, we see a visible increase in the goodness score for each teaming suggestion. We show results similarly for M2, which is semantic matching. On the left, we see that the skills needed for each proposal are displayed with various codes. These codes represent the classification system provided by ACM. And finally, we show results for M3 boosted bandit learning for the same researcher. For each selected use case and method, we ask participants for feedback on relevancy of teaming suggestions and their utility, along with any additional comments. We track the given inputs and their survey responses for further analysis. Similar to use case 1, we also have use case 2. We select a proposal from a given list and a matching method. As an example, here we select a fairness and AI-based proposal and select M3 as our matching method. And the output is a list of teaming suggestions along with goodness scores. In use case 3, we give a research interest from a given list and select a matching method. As an example, a user may choose to see AI-based proposals for the method M3. Or an interest such as quantum and a different matching method such as M0. This concludes the demonstration of our tool. For more details, please visit our website here. Thank you for watching.